So hello everybody, this is Nacho, I'm YProm's CTO. Today we are conducting a new lightning talk. In this case, it's going to be Matheus talking about optimizing machine learning development with AutoFeature engineering. If you have any questions, please post them in the chat. I will be acting as moderator, and when it's time for question and answers, we will go through them. So Matheus, if you're ready.
Okay, so thanks a lot, and we will discuss today about how we can do auto-feature engineering. So it's a very important step in the data science pipeline, and how we can automate this using a framework named Feature Tools. So first things first, you can see my screen changing the slide, please. Okay.
We can see the slides, Matthew.
Okay, it's not changing for me. Just a second.
Yeah, it's not changing.
Let's do it again. And okay, now it's changing. So first things first, let's define what is a data science roadmap. So every time that we do a data science project, a data science product using machine learning, we need to follow some of important steps to develop this new platform, this new feature, or this new product. So we need to pay attention in data collection. That is where I have the data stored and how I collect this different information from different sources. We have also the data cleaning step. That is when we merge and when we collect different information from different places. We need to pay attention in some standards, or how the data, how some columns came for us, and we need to handle with these different standards. We do some exploratory data analysis. That means every time that I have new data, I need to explore and see what kind of information that we have in that data, and what kind of story that we can learn from the data. And once I clean it, once I understand it, once I have knowledge about the problem that I want to solve with data, we can go to the model building. That feature engineering and model development and all the machine learning code we do in this step. That means model building. And once we have everything done, we can go to the model deployment and ship this product in production, and have our product ready to consume. So I want to discuss with you a little bit about the data preparation problem. That we have a survey in Forbes that told us that data scientists spend almost 80% of their time on data preparation, because we have data came from different places, from different standards. So we need to pay attention, clean the data, and have a unique way to display this information. So I have an example below of a data set with mass information. So for example, for date, we have different standards related to the date field. Also with name, we have everything lowered. We have some missing values in the last line, the last row. And also for the note, we have some unnecessary characters there. So that's why we need to have this cleaning and feature engineering process. So this feature engineering process is a very important step, because we need to use domain knowledge of the data to create new features, create new information that machine learning model will learn patterns from it. So that's why we need to have everything cleaned and everything done to feed these models and build our products. So every time that I handle with features, every time that I'm looking for it, we have different types feature to pay attention. So I have, for example, numerical ones that I can split into continuous and discrete information. For example, I have a continuous information like a salary, a wage of a person. I have discrete information like the amount of cups of mugs that we can have. We can have also categorical features. We can have date or time information. We can have mixed information itself, or anything else that we can use like text, images, sounds, and so on. So for each type of variables and features, we need to pay attention to how we can handle it and how we can do feature engineering for each one. So that's why we spend a lot of effort and a lot of time just in this part of the process. So when we have different features, when we have different information, we have some steps of how we do feature engineering. So first of all, when I'm saying feature engineering, I want to be known that feature engineering means feature creation. So every time that I'm creating features, I'm extracting features from dates. So for example, if I have a column date, I can get information like which year is this date time, which month, which day, if this date time belongs to a weekend, or which is the weekday that this date is related. So we can create from a single value 4, 5, and lots of different information from it. And also I can extract features from mixed variables, mixed features. So I can combine them and transpose information, or dividing, taking the ratio from one to the other. And when we do that, we have some problems related to missing data imputation. So when I create a new feature from mixing other features, maybe in some cases we don't have information, so we will have this missing data, and we need to input new information, because the model needs to have this information to be trained and predict things. We need to encode categorical features, because a machine learning model is a mathematical model. So math doesn't understand what is a string. So we need to convert it into a number and then feed the model with it. So we need to do this this categorical variable encoding. We need to do some numerical variable transformation as well, because we have some different ranges and different features with different ranges. So we need to standardize these things. And when I'm facing some numerical variables, for most of the cases we have outliers as well. And outliers, they are samples, records that are very far from the normal distribution. So we need to pay attention to that when we are developing models, and a lot more process to do feature engineering. And for each step, we need to code a lot of pipelines, and this could be very messy once we have a lot of features to process. So any question until now?
I do have a question. So you're
Okay.
extracting features from dates and extracting features from mixed variables. Are dates special in any way? I mean, why from dates and not from other data types, like extracting features from floats, integers, strings?
Every kind of information is important for us. So for example, if I'm doing a model that I want to predict the future value, not the future value, but the amount of money I expect to to have in a certain time. Imagine that I'm a retail company and I have seasoned periods of time. So here in Brazil, we have a special day for Mother's Day, and the retail earns a lot of money in this specific period of the year. So maybe having this information in our model could be interesting for us once we have a seasoned period of time or not. Or maybe if I want to give credit in a retail company and most of the people buy things in the weekend, so maybe know that that specific day is a weekend or not could be nice.
Okay, let me ask one follow-up question with that. I understand how you can extract features from dates, like weekdays versus weekend days. That information might be very valuable for prediction. Can you also extract features from other data types like integers, whether it's an odd or an even number, whether it's a prime number versus a compound number? You can extract features of any data type.
Yes, once we have the data and we have this domain knowledge, I can create features from that. That's why the domain knowledge is important to the feature creation process.
Okay, thank you.
Okay, so once we know, we understand that this feature engineering process is important inside our machine learning and data science project, I want to introduce you a framework named Feature Tools, which is an open source library to perform automated feature engineering. So every time that everything that we discuss it until now, we can automate using feature engineering, automated feature engineering frameworks. And one that I want to show you is this Feature Tools, and it supports a lot of functionalities, a lot of things, including feature selection, feature construction, using relational databases to create new features. So I can show to this framework all the tables inside a database that have a relationship and build features automatically from them and more. And here is an example of how Feature Tools works in a nutshell. So we have here below a table with a product ID and a price. And I use Feature Tools to create a relationship between the product table with the order table. That is the second below here. So for a unique ID, I have two different product ID, and each product ID have a price. So Feature Tools find the relationship between these features, this table, sorry, and aggregate, merge the information from for this order table. So for example, I have this order ID, and from this order ID, I have two different products, and I have a product price for each one. So once I have this information here, Feature Tools will sum automatically the information from them. And the table above, we can see that this framework created a new feature named sum of product price and aggregate information related to a customer. So the same customer has different order IDs. So this customer bought a lot of times, and Feature Tools will take the average automatically and finally have the aggregated information for a customer. So I have a product ID and a product table, and this product table shows us the price of a product. I have an order table that is related to the product table, and for different orders, I have different products and the price for each product. And for in an order, I can bring the information into the clients, into the customer table, aggregating this information in this final table. So we can do this manually, writing some SQL queries, but feature tools can do this automatically for us, combining everything and merging them together in a unique table. So I want to explore a business case from Home Credit. So Home Credit is a financial company that gives loan to the unbanked population by providing a positive and safe borrowing experience. So with Home Credit, we will work with different kind of information. So we will have information about each loan application inside Home Credit. So this is a table. We will have a table with information about the client's previous loans with other financial institutions that reports this information to the Home Credit. We will have also previous applications for loans at Home Credit, monthly data about the previous point of sale or cash loans for each client, and a lot of more tables. So here we have an entity relationship diagram for each table. So how they are connected, the ideas that builds this relationship between every single table, and we will show to feature tools this entity relationship, and this framework will build everything by itself. So before we go to the coding steps, do you have any more questions? Okay, so before going to the feature tools framework, I want to show you how we do feature engineering manually. And then we can compare how feature tools work. So I have an environment here in Google Colab, and I can share this link here in the chat, and you can do these things by yourselves and see how it works. So first of all, we will use it using Python. We will do it with Python. And first things first, let's import all the libraries that we will use to this project. So I will use pandas to handle with data frames, NumPy to do the math stuff, Matplotlib and Seaborn to plot some things, and just warnings to suppress some warnings that are unnecessary for us right now. And let's download all the information that we have for this Home Credit problem. And once we download it, we will see them right here in this structure. Okay, so every single data is here. Now I want to load a data frame related to previous loans to give an example of how we aggregate things. So I use pandas to do that. And once I loaded the data, I want to see the first 5 lines. So that's why I use this head method. And here we have information related to a client, a customer. Then we have a unique ID related to this bureau company. We can see if this client has an active credit and a lot of other information. So let's aggregate just one feature and see how we can do that. So we can use the group by method to do that. It's very simple how we do this. So I can take this data frame. Let's call these tables as a data frame, and I use this method group by, placing here which is the unique ID that I want to group, and which is the column that I want to perform an aggregation. And the method that I'm using to aggregate is count. So what I'm doing here is how many occurrences I have for a single customer inside this table. So I will say that this feature is previous loan counts. So for every single client, I can say how many loan counts they have, and I can aggregate this information inside the application data that I want to use in the future in my machine learning model. So read the data, merge the feature that I created here with the application trained data set, and fill all the missing values with 0. What this means? There are some unique IDs that I can't find inside this Biro data set. So when I merge these different data sets, we will have misinformation from those that I didn't find. So if I don't, I didn't find this information related to previous loans, I can say that this specific ID didn't do any loan in the past. So that's why I want to fill this information with 0. This thing, do this thing make sense for you?
Yes, I think it's pretty clear. You're counting how many loans you had per client, and if there are no loans for that client, you're assuming that there has been 0 loans, right?
Yes, perfect. So that's why we need this domain knowledge to understand what is happening here.
Correct. How big is this data sets that you are loading here?
Let's check right now. So for application, I have almost 300,000 rows and 22 because I aggregated an information, but 22 columns. And we have information like we have these IDs, this client ID, we have the target that in the future we want to predict, and all the information related to the application. And when we go to the final columns, we will have the column that we already created. So let's go deep. Let's go deeper and not only take the count, but also aggregating some information like taking the count, the mean, the max, minimum value, and sum for all the numerical features from this Biro data set. Not for a single column, but from all the numerical columns. Just rename because it's like we don't have this explicit way to say that this count belongs to this credit, this mean belongs to this credit. So we need to rename some columns just to have these things corrected. So now we can say that from the Biro data frame, we have this feature, this credit, and we take the count for this column, this feature. And we did the same for the mean method, the max method, and the other aggregation functions that we use it. And once we have this information created, let's merge into the application dataset, doing a left to join. And now we have 183 columns in the final dataset. And once we develop these new features, let's see how this feature can explain our problem, our target that we want to predict. So let's take the correlation from these columns with the target that we want to predict. So correlation means how strong is a relationship between different columns, different features. So if I have a high correlation number, that means that one feature can explain with a strong level the other one, and when this correlation is near to zero, these features, they are not related, and the range from this number could go from -1 to 1, when the opposites, the far right and far left are strong, has a strong correlation, and near to zero means zero correlation, or they don't explain each other. So we have a certain level of correlation. It's near to zero, but if we see the correlation between all the other features that belongs to the application data set, they are similar to that. So the features that we created can explain a little bit what is happening with the target that we want to predict. So let's create a function just to aggregate this method and use this for different data sets. So this function named aggregate numeric will do the same thing that we did in the previous pieces of code. So we'll take a group by for the numeric columns, rename the columns, and print information. And we can do that for all the data frames that we loaded before. And now let's do feature engineering for categorical variables. I can have a feature named credit, a credit active, and we have four different informations. We have a categorical information named active. We have a categorical information named bad debit. We have a categorical information named closed, and the last one is sold. So this feature has a string information, and we want to transpose it into a numeric feature. So the method that we use to do that is get dummies. So we will transpose and have a binary combination of each information. So for credit active, if I have this label active, I will place 1. And for all the other fields related to credit active, I will place 0. So in this first line, we can see that the credit active is closed. So all the others combination will have this number 0 belonging to it. So we can say that this row, the final result of it is that this specific ID has a closed credit active. And we will do this for all those categorical features. And that's how we can turn the string information into numeric information to feed our model. So let's do it. And once we transform this information into numeric, we can do all the numerical feature engineering process, aggregation by sum, mean, or maximum value, and so on. So we combine a different kind of feature engineering into a unique type of feature. So we took a string, transformed it into a number, and then aggregated the information by an ID. And once we did that, let's aggregate into our final data set, into the application data set. So now we have 229 columns in this step. So we build more than 100 features. And let's build a function to do this automatically for the categorical features. And we can do that for all the data frames that we have. So we did this only in the Beetle data frame. So we can load all the other data frames and run this function to create numerical and categorical features. So that's what we will do here. So I load this Beetle balance data frame and run the categorical function, the count categorical function, and this will count everything related to categorical features. So we have 3 columns in this data set, and now we have, let's see. We have 16 columns, so we have now 13 new columns in our process. Then we will aggregate the numerical features and keep doing this for the other data frames. So just to do a quick recap, so we calculated numeric information, numeric statistical grouping every numerical information by each loan. Then we made value counts for each categorical variable and also grouping by loan. And then we merged all the stats in the value counts for the loan data set. And then we calculated numeric features, numerical stats for the resulting data frame, grouping by the client ID. And we did this for writing the code for every single data frame. So now we have all those features, all those functions. Sorry, we can run for all those data frames and have the final data frame ready to be ready to the machine learning model. So we deleted all the data frames that we created before, load the raw data frames with the raw features, run the functions, and have all this feature engineering process done and aggregated the new features. So while this thing is running, do you have any question? Anything to point?
I have a question about the outliers value.
Okay.
When you figure out that there might be some outlier, is there a rule of what to do with that? Like, oh, this might be some bad data, or this might be valid data, so that let's consider. I would like to understand the approaches that that we might do with the outliers data.
That's a good question. Thanks for making this one. And there are a lot of ways to handle with outliers. If we have very, very few cases, cases which are outliers, we can drop them from our data set. Less than 1%, for example, is outliers, we can drop them, drop the row as an example. Or we can, instead of using mean, average, instead of using average in this aggregation methods, we can use the median method, because when we took the average from a column, we are not robust enough to handle with outliers. So if we take the median, we will solve the distribution and take the exact point that cuts this distribution between these both sides. So we won't this problem with outliers won't happen. Or we can do a thing named interquartile range. So I can compute the standard deviation for this numeric feature, and everything that is above threshold, for example, 1.5 standard deviations from above and 1.5 standard deviation from below, I can place the threshold for the outliers. We won't have it outliers anymore. So there are a lot of ways to handle with that. I said 3 ways. if you want, we can discuss this later. I can send you some articles how to do that.
Interesting. Thanks for the explanation.
Cool. So when we started doing our process, we have 122 features from the beginning. And after the feature engineering process, now we have this amount of new features. So from the raw features from different sources, we build a lot of information, and we can use this to train a machine learning model. So in the following pieces of code, we will do the same for the testing data set. That is the data set that when we build our machine learning model, we want to test if those predictions are good enough or not. So we will not follow these following steps of code because we won't train any model today, but we will repeat these steps, these machine learning steps, the feature engineering steps for the application test data frames. So this is how we do manual feature engineering. And now I want to show you how we do this using feature tools. So keep in your minds how we build things here in the manual way. And now let's see how we build this into the automated way. So we'll start feature engineering in this feature tools framework in this environment using the pip method, and also download all the data that we will use. They are different environments. That's why I need to download it again, because I don't want to mix things. Let's see if downloaded. It's downloading the data as we did before. This data is public. So when you execute this code, you can download it too, so you can reproduce all the things that we did here, we are doing here. I believe this is the last data set that we are downloading right now. Yes, it's the last one. Cool. So let's do the same process. Import the libraries that we will use, and here we will do a different thing from the past pieces of code. We will read only the first 5,000 rows, because feature tools will create lots and lots of features, and when this framework starts computing the information, the final data set will be very large, very heavy, and we won't reproduce this into this environment. So that's why we need to have a robust environment to do that. So I will do this only for the first 5,000 rows, just to show how this framework works. So I will read all these data sets and limit to read just the first 5,000 rows. And if you want to read the article later, I reproduced this experiment with all the data that we have there, and you can see the results there when our article be published. So we are reading these data frames, and after reading it, we will merge them, we will combine them. And just to say that these pieces of data is training data and these pieces of data is testing data, we will create a column named set, just to say that this pieces belongs to training, these things belongs to test, because feature tools will compute the information for both data sets in the same time. That's why we need to merge them. And then we will split them again. So let's do that. And okay, so let's start with feature tools. When we are working with feature tools, we need to define three things. We need to define what is an entity set. We need to define what are the entities, and we need to define what is the deep feature synthesis, which is the method that feature tools use to create features. So let's start with entities. Entities is every single table that I want to create new features. So I have a database. This database has a lot of tables, and each table is an entity. So I need to say to feature tools what are the entities that I want to use to create features. And the set of entities is an entity set. So let's say that the entity set is related to clients. So I will create an entity set. And for this entity set, I will say which is every single entity. So I have an entity named application, which is this app data frame. And I need to say which is the ID, the index that this data frame has. And also for the other data frames that I want to use. And there are some cases that my data frame doesn't have a unique ID. So a feature tools can create this unique ID for us. So I can say that I want to create a new index and name, and give the name for this new index. So that's what we did here. So we can use data frames that have unique ID and data frames that don't have unique ID, and combine them into a unique entity set. So let's do this. And here we have an entity set ready to create the relationship. So until now, we just said feature tools that we have entities. And now we need to say to feature tools how the entities are related to each other. So that's how we build the relationships. So I use this method, add relationship, and I say, okay, I have this parent data frame named application, which has this unique ID, and I have a child data frame named Biro, and this Biro has a unique ID named this one, and this unique ID from Biro and this unique ID from application, they are the same thing. They have relationships, so I want to say I want to give this relationship between them. So we will do this for every data set, every entity that has a relationship between themselves. So once I did this, we can see the entity set again with the data frames, the entities, and now with the relationship between every single entity set. So until now, we didn't code anything related to aggregation and transformation methods. We just place it here, which are the data frames that we want to use and the relationship between them. So what we will do now is say to the feature tools which methods that we want to use. So I want to plot an entity set diagram. So if you want to place them into a documentation or and store this information anywhere, you can plot this diagram, and feature tools does this very easy for us. Okay, so once we have all this relationship created, let's say about these feature primitives. And these feature primitives or feature tools, they are the functions related to aggregation and transformation method. So aggregation means taking the average, the minimum value, the maximum value, the skew of a column, and so on. We can see all the aggregation methods that feature tools has. So we have compute the first occurrence, the first value of a unique ID, a skew, the most common, the number of truths for a column, the entropy, maximum value, the mode, the first time since anything happened, and so on. So we have a lot of different primitives to use. If I'm not wrong, we have more than 90 primitives, so we can compute lots and lots of information from feature tools. So this is aggregation, and we have also transformation primitives. So I can compute the rolling count, the first time since a previous occurrence. I can compute the day from a date column. Hover sign, compute the distance between different coordinates, number of words for a single document. So we have lots and lots of functions to computing features. So let's say that we want to use this one. These ones, I have some standard deviation, maximum value, skew, and so on. And for transformation primitives, I want to compute the day, the year, the month, the weekday, and hover sign information. And once I define what I want to use, I can finally use the deep feature synthesis. So as I told you before, the deep feature synthesis is the method that feature tools create new features. This is built from an article for an academic research. And when they developed the method, they build the feature tools to do this automatically. So for feature synthesis, a deep feature synthesis, we need to say which is the entity set that I want to use, which is this ES variable, number of jobs, the number of cores from my processor that I want to use to process all the information. So if I use -1, I want to use all the cores available to process. The target data frame, so I have all that entities. So I want to say that the final entity that will receive all the new features will be the application entity. The methods that I want to use, the aggregation primitives and the transformation primitives. I can ignore some columns because I don't want to compute the mean of an ID, for example. So I can say that the columns that I want to ignore related to application entity are these two. I don't want to compute anything related to the unique ID and the target that I want to predict. And the same for zero and zero balance. Variables that I want to say what is happening under the hood, the amount of feature that the feature tools will create and the time remaining to the process. And I want to use, I want to focus to compute the mean primitives. So once I start running this step, the framework will compute 2,212 features, and that is, and they are more than the 300 that we build in the manual process. So the thing here is that we loaded the data set, we defined the information and how the relationship works. And once I defined how the relationship works, I set all the methods that I wanted to use. And once I defined that, I said to feature tools, okay, calculate everything from these entities and we will have this amount of features just writing few lines of code. So while the features are calculated, do you have any questions? Okay. But okay, Matheus, why do we use feature tools? In the beginning of the presentation, I said that a data scientist spend most of more than 80% of their time doing this step, feature engineering. Not only feature engineering, but feature cleaning and all the preparation before doing the feature engineering. But I can say that most of the effort that we spend is related to this feature engineering process, because this thing is very creative. This process is very creative, and we need to understand the domain. We need to have the domain knowledge. So I need to understand the business that I'm working on, and once I have the business understanding, how I can create features that make sense to the business. And this part of the process, we spend a lot of time, because I can imagine new features, I can code new features, I can test the new features, and then see if this feature is explainable or not for a model. So instead of spending a lot of time doing this step, I can use a framework to do this automatically for me, and I can spend effort and all the time that I have just testing if these features that were created automatically, they are reasonable or not. So that's where the domain knowledge could go. I can spend just maybe a couple of hours instead spending maybe weeks or months creating features. And once we created a lot of new features, we can test if they are reasonable or not. So time is money, and we want to spend less time doing nonsense things and focus on the things that increases the performance and the final product that we want to ship. So that's it. We built for 5,000 rows this amount of features in 1 minute. So let's see some examples of features that feature tools created for us. So we have this unique ID related to application dataset, and feature tools look at for the installments and install how many times this ID appeared in this dataset. So it took the count of installments. From installments, we have the amount installment, and feature tools computed the maximum value for this feature. And another cool example is that feature tools combined the features related to the credit data frame and the previous installments data frame, merged the information and took the sum of the result. And here we can see all the other examples that feature tools created for us. So we have the raw features, and now we have lots and lots of new features, more than 2,000 features created here. And then we can use these features to train a machine learning model and see if they are reasonable, if they are explainable or not. So that's it. The upcoming talks will be related to the machine learning development. So we will use this data frame created from feature tools and see if these features, they are good or not. So we will have a machine learning model. We will train this model using the raw features, the manual features, and the automated features, and see if these things could fit in our machine learning pipeline. So thanks a lot for your time, and do you have any questions? I'm available for it.
Yes. Hello, Matheus. I have one question related to the one of your first talks related to data preparation. And then I understand that this is a crucial task for machine learning engineering. What is the best approach and the best tools to deal with this, let's say, big issue, preparing data, cleaning data, and make sure that we are working on a good quality of data?
Okay, that's a good question. The key point for a machine learning model is feed this model with data with good quality. So we need to be aware once our model is deployed, how the data is coming, because if the model is not aware about that, let's say that we have a numeric feature with a range from 0 to 10, and something in the process of creating features happen, and the model received this feature with a value of 1 million. So we need to pay attention in this step of process. So there is, we have a framework named Great Expectations that we can insert this into the data engineering pipelines to measure the quality of data that we are using. And once something strange appear into the process, this framework will raise a flag and say that something strange is happening and how the data engineers need to work to solve that, because our model can make wrong predictions and maybe break the service when these things happen. So that's why we can use this framework named Great Expectations. So did I answer your question?
Yes, very good. Thanks so much.
Okay, another question?
Well, if we don't have any more questions, I would like to add 2 more comments. The first one is that Matheus mentioned that this will be published. It will be, the content of this call will be published as a blog article in our Medium blog that you can search it as YPRAM Medium blog and you will find it. If not, from ypram.com website, it's linked in the footer. The second thing is that this is the first of a series of talks. This is the first one of 4, right?
Yes.
So stay tuned for the next calls that will be coming soon, as well as the corresponding Medium articles that will go through it. Matheus, thank you very much. It has been very, very good presentation.
So thanks a lot. And any question, you can send a message, an email, or anything else. So have a good night, and see you on the next talk.
Thank you, Matthew. See you all. Bye.
Thank you. See you. Bye.
Bye-bye. Thanks.
Bye, thanks.